Hello and welcome again to British Academy for the Python graph series. In the last video we have built the Dijkstra's algorithm, pretty much the accountant in pathfinding, found the absolute cheapest path on this map here by counting every single penny. So that's why we call it the accountant. So it works perfectly. What else do we need? Well, it has one flaw. It did not take into account this h equals 35, the so-called heuristics. It explores all the directions equally. So that's like, for example, if it looks for a road going to the north, it simply checks all the roads, even the north ones and the south ones, and yeah, this kind of wastes time. You can imagine yourself. So today we are going to fix that, and we're going to build a star algorithm, which is pretty much like Dijkstra but with a compass. So it doesn't just know how far it has come, so to say the G, but it also guesses how far it has left to h. So pretty much if you take a look at this graph here, for example, the h equals 5, and you see the h is always increasing because it is simply guessing when we are going to arrive to the target, in our case P. If you take a look at this one, h equals 3, but it's actually 50. Okay, so yeah, imagine that a star is Dijkstra with a compass, so to say. So let's see what we have so far with Dijkstra: the raw data, the solving, the optimal path, highlighting, and then here this was our highlighting the data. You see this was the Dijkstra A, C, G, H, P. And now we're going to rebuild this one from Dijkstra into a star. So bear with us for the a star. So starting with the a star, I have promised that we're gonna build upon Dijkstra, and I mean it. Yeah, what do? We name our function first from solve Dijkstra to solve a star, and also this one. Then we take a look at the Dijkstra, the solve a star, and we start thinking why this while PQ is within the for loop that actually reads stuff. And the question is that this is a mistake. So in the previous video, I hope someone one day will notice it, and I'm going to point it out to this video that this is how to fix the mistake. Okay, Shift and Tab. Next, what do? We have to read everything from here. So far we're only reading the first part, A, B1, for example, the edges. Yeah, we are not reading the nodes and their heuristics, and we need to find a way to read these kind of things. And it's going to be a dictionary, and it is going to be a nice dictionary, so to say. Yeah, so it's gonna be node lines, and it's gonna take the lines, but not exactly. It's gonna start from where the lines finished, so not 1 but 1 plus number of edges, and it's going to finish to minus 1 in English. Okay, and then we're going to read them one by one. So for line in node lines, parts will be line.split. I mean, splitting them would deliver these two would be the first part, and this would be the second. So we can call it, for example, no, parts is good, or we can call it edge and heuristic, for example. So it's more understandable. Edge name heuristic weight, and then heuristic. I mean, this one, heuristics, and this way with the edge name would be actually parsing to int and then heuristic weight. This is understandable, and understandability counts. Let's take a look. Yes, we have it. We successfully managed to read it. Great, let's continue. So the thing with Dijkstra is that Dijkstra starts on 0. Should be like this and like this. So in Python, okay, I probably coded something in C# and I forgot about stuff, but yeah, this is how it should be. Dijkstra starts on 0, but on A* we have a guess already, so we can improve it. How do we do it? We change a bit the PQ to start F and not to 0, but to start F. And what is start F, you ask? And that's a really fair question. Start F is 0 plus just heuristics dot get start 0. Okay, this 0 plus, you're probably thinking, why do we need it? Okay, this is kind of information for us, what's going on. If this thing by itself is not enough to tell you that it's, if the start doesn't exist, then we're gonna use a 0. It's somehow an information that is not very important. Okay, let me think what you think about this, adding a 0 like this. I like it. I'll keep it, but I guess I'm one of the very few. Okay, so now with the heuristics. Now we are in the core logic here, while PQ. And what do we do in the while PQ? We implement the magic formula. I'm going to write it here. F equals G plus H. So go plus heuristics. Forecast equals go plus heuristics. This means that, let's say we have reached up to this point, so the real one is 5 plus 2, 7, and the heuristics is this 10. So, and the 15 to reach the 10. So this is pretty much the A*. It's not better than Dijkstra, just once more pointing it out, it's faster. It doesn't go all around, and our heuristics is the reason why it doesn't go all around. Okay. This thing here, the heap push, is something that we have to fix into something better. But I'm going to start from the beginning. Okay, so current F, current node, heap pop PQ, that's great. Then current node end, okay. This success I'm going to keep. So now the more interesting here, optimization part. Let's say, for example, the following: best known G, is the cost so far of the current node, this one. And best node F, this is also what we need. And it's going to be the best known G plus heuristics, this one. Heuristics get current node or 0. This is actually for the case where we don't have heuristics for all our edges or for all our nodes. I mean, edge is the stick and node is the circle, so the city. Okay, further, if current F okay, current cost, I'm going to change to current F. Yeah, makes sense. And current node, okay. If current F is bigger than best known F, then continue. Great. Hope you understand. Continue with returners on the PQ, and we're gonna change with the next one. Okay, now for neighbor weight, we don't have a comma here. How this code was actually working before? Anyway, in graph get current node. Yeah. So here we're gonna say new G, because this is our function G plus H for the heuristics. New G equals cost so far of the current node plus weight. Great. So here I'm going to rename it for new G, cost so far get and for neighbor, should I put it like this? Yeah. Or neighbor, no, I'm sticking with this one. Okay, so if new G smaller than cost so far, then the party starts cost so far neighbor is equal to new G. Yeah, we were renaming everything. So cost from neighbor came from neighbor is actually the current node. That's great. And now pretty much the highlight of, I'm going to put highlight of A star is this one here, and it is actually new F equals new G plus heuristics dot get n and 0. Yeah, fair enough. And of course heap q, heap push pq. Of course we are pushing the new F and the neighbor. Shift and tab, everything runs perfect. I'm going to view it in Zen so it's better for the video. And now let's give it a try. Optimal path ACG HP, ACG HP. Great, this is the optimal path, even with Dijkstra, even with our beloved algorithm. But the thing is that it's good if we can prove it somehow. So let's change or prove that actually A star is somehow smarter than Dijkstra. I mean, the idea is to improve. So prove to improve. So in our map, actually ACG is the shortest ACG. Yeah, true. Because node C is actually very, very close and Dijkstra loves it. But what if we knew in advance that node C is really dangerous? Let's say somehow that there are some, I would say, criminal elements around the road, or that it's like a broken road, yeah, let's assume it's a broken road. And we cannot change the physical road distance because the road exists there, but we cannot change it. But what we can do is we can change the heuristics of the algorithm. So, yeah, the C would be, let's find it here. The C is 20. Let's write a few lines like this. Yeah. So this way the algorithm wouldn't even actually look at this one. So Shift and Tab, at least this is our idea. So A star, and I think we found something else, A, B, E, F, B. Let's give it a try and highlight it. Yeah, A, B, E, F, P, because of the heuristics that we have put here. Our algorithm just said, okay, I saw a lot of 9s, I'm not happy, obviously something wrong with this road, although I like it because of the 5. It simply said, yes, going up to there. So it actually makes sense. The algorithm itself completely changed its mind just because of the heuristics. It didn't bother to go further after it because of a lot of 9s, and it took the longer path to avoid node C. So yeah, Dijkstra would have entered the trap because it doesn't take a look at the heuristics, but our algorithm actually avoided it correctly, and this is what we did. A, B, E, F, and then P. Okay, let's summarize. So in summary, today we were talking about A star, building over Dijkstra, showing the old code from Dijkstra, and improving it up to reaching A star. So generating graph plot is the way we generate the graph plot. Raw data is our initial raw data as it was in Dijkstra. Here you see the C20, and then we had the heap queue. Then we had a few changes that we have done. For line in lines edge name heuristics weight equals to line split. This way we managed to record also the heuristics in our data, which wasn't done for Dijkstra. If you are watching the Dijkstra video, you probably have seen that here everything was within the loop for the fall like this, and it was a magic how it worked, but it worked. So yeah, somehow wrong code works as well. Strange that no one wrote anything about it, but doesn't matter. Okay, so after this one, what did we do? The second thing was fixing the priority queue with start F and start, which is pretty much good. And then we took a look at the loop itself, and we made sure that we always take a look at the new F to be new G plus heuristics. And this is the formula for A star here. A star is like this, A star F plus G. And in the end, this one is also from Dijkstra reversing. Let's take a look. Yeah. First, we saw that our preferred path is ACG HP as it was in Dijkstra, but in order to show that our code actually works, what we did is we changed the C heuristics from 20 to 999, which means, for example, that there is a roadblock or the road is broken, so we have to avoid it. And running the A star, we saw that we actually avoided it, going ABEFP. Highlighting the data looks like this, ABEFP. And we see that although this road is not the shortest one, we have a 50 here, which is obviously not shorter than 522. Based on the heuristics that we have implemented, we don't even change this road here. We don't check it because, yeah, we have something really wrong into C, and it means that point C should not be checked, or this road should be avoided. So this way we understand that A star actually reacts immediately, abandoning a short road because the heuristics warned of a high cost ahead, and delivering, diverting, so to say, the entire path to the north. So yeah, with A star we combine two methods, heuristics and shortest path, which is good in this way. Okay, so far so good. Enjoy the rest of your day or night by British Academy, and take care of yourself. Goodbye.